everyone. This is a video describing how you can make a room temperature superconductor in around. So I have with me today Preetha Mandal, who is a PMRF fellow, and this synthesis has been devised by Dr. Rekha Mahadevu, who is not in this video. And Preetha will be showing us, Preetha has greatly improved upon the synthesis, and she will be showing us how to get this thing done. The details are also available on Chem Archive, and you are welcome to follow them up on there, and we'll describe other details towards the end of this video. So by 3 minutes flat, of course, there's a caveat. This is how less than 3 minutes to make the material, but actually much more to deposit a reasonable working film of it, but you'll see. But it's still not an intimidating method. So what Preetha already did in the beginning of the video, when you just saw her pouring the measuring cylinder, that was C-tab, that has been preheated. Temperatures are mentioned. She is now adding a small amount of NaOH to it to adjust the pH range close to 7. And as soon as she does that, now she commences adding the other reagents. Those are ammonium bromide and potassium iodide. So the pH, as you can see, is adjusted close to 7. That was a piece of pH paper right there. And now she commences with the addition of the other reagents, ammonium bromide, potassium iodide, and eventually silver nitrate. Now the silver nitrate is a critical step that has been pre-measured over here in that little file. So she adds all of the contents, and as soon as she does that, she starts a stopwatch with her other hand. So this is a critical step. As you can see, the stopwatch has started, and the reason for doing that is because you need to wait for a precise amount of time, which is around 90 seconds. She keeps ready a solution of HAUCl4 by her side, as well as the sodium borohydride. Now the sodium borohydride, please do be very cautious about. It has to be prepared fresh, it has to be in topmost quality, and this is also at ice cold temperatures, as you can see. So now it's just a question of waiting. Both are kept ready in readiness for addition, and she stirs it in the meantime. So we are just waiting on the clock here. As you see, the solution seems visibly clear. There is not really much going on over here. If you observe closely, I can give you a small zoomed in view. What Preetha will do now is go around adding the other reagents now that her time is up. That's the NaBH4 first, the gold second. They are added in quick succession. You observe a slight color change in the material, not a slight rather, you observe the emergence of essentially the color of what we are calling essentially the gold silver colloid. As you see, this is a fairly colored substance. Now what Preetha is doing now is she is adding IPA, which is 3 ml into the system. At this stage, this is a pre-precipitation of sorts she is doing to the gold silver colloid. This enables her to now take this material and start the centrifugation process that we describe next. So that's essentially the first part, and now she is transferring this into Eppendorf tubes over here in her hand for further centrifugation. So you see also that, based on this, and we'll show you a spectrum momentarily if you have not seen one ever, which is that these materials are colored, they are lossy, they are not unlike normal metal. So whatever we have mentioned before, the properties of an R1 resonance which seems non-lossy, is entirely collective behavior rather than the behavior of isolated clusters or isolated particles, which is what we have in this particular solution. So note that while making this addition, Preetha also adds a small amount of acetone into each sample, into each Eppendorf, as you see here. So this is the neat solution coming in over here. She is putting around 0.5 ml into each Eppendorf, and to each Eppendorf she further adds a certain amount of acetone, which dilutes it basically by a factor of 2. So she is going over to 1 ml. So 0.5 ml of acetone comes in to each 0.5 ml of sample. So 1:1 ratio. Post that addition, and when you're not stirring this, the system actually does transition into a gray state. As you can see, the Eppendorfs which are sitting on the side, which were loaded a little bit earlier, look slightly different in appearance compared to other Eppendorfs. So this is basically a two-stage pre-precipitation. We'll see the results when we centrifuge them. Yeah, we are now reaching 7,300 RPM or so, which would give us the desired RCF, and there's still 3 minutes to go, so you would have to naturally attune this to the precise conditions that are there in Lawson. So the time is up, the centrifuge is now spinning down, and we would then be transferring it immediately to the glove box. The centrifuge has now spun down, and Pritha will now be removing the samples from inside. She will just pour off the supernatant into the base beaker, and the precipitate is just dried coarsely on a tissue paper and then moved into an inert environment chamber, where it is dried further, first purged under vacuum and then moved directly into the glove box. This entire operation is a bit delicate, it has to be done rather rapidly, and you'll see. This is just to remove the excess liquid. Sorry, I'm trying to focus here. Not getting a good focus. I think I won't get a good focus like this, but you can roughly observe that there is some amount of precipitate in this Eppendorf. It will help actually if you leave an Eppendorf on the tissue. Yeah, now this is a little easier to see. There we go. So normally this delay is also a bit too much. We now move them to the inert box. So we are now at the glove box, and as you can see, we are right now working with an oxygen ppm of around 0.3. That's what the sensor says. It's a little below the sensor's trusted threshold, but it means it's really low. The water levels are also factored. What we'll also do at this stage is just quickly show you the spectrum. Details are naturally posted up on archive, and they will keep getting posted as and when the need arises. We'll just quickly show an absorption spectrum. This is just done on a motion optic spectrometer. This is a water aliquot, one of them which was not put inside, being collected. So, as you see, it's a fairly broad and shapeless mass that you observe. This is essentially the hallmark of whatever again we are terming as the AUEG colloid. You'll see that this is actually quite a colored material. This is what you would anticipate it to be, given that it's a gold and silver based material, and it bears no traces of carrying anything like what we have referred to in the past as R1 resonance. But that bit is now done. The essential explanation, though, let me add. So essentially this is the spectrum, and essentially the important part of it is that these consist of isolated clusters of gold and silver floating around, and they do not carry the property which this AUEG material is all about. Rather, it's a collective property which emerges when you have them embedded in a certain disordered fashion. Now I have with me Dr. Anand Sharma, and he will be moving the samples inside the glove box. They'll be coming in via the larger portal there. They have been, as you know by now, redissolved into chloroform and concentrated somewhat. So this is So we will be doing the deposition on these 4 probe electrodes. These actually, as you can see, have 6 digits in them, and the spacing there is 100 micron gaps between the fingers. So now the sample would get deposited onto them. Just checking the orientation there. So it's not very clear in this picture, but if you are able to see, then the sample is actually quite dark in color. That is not too easy to observe because of the lighting, but essentially at this stage you will observe that the sample is dark when you are doing it. So essentially now the protocol will be that the sample will be drop cast onto these electrodes. The inert box is a little clumsy. This is again coming out from a chloroform solution, and subsequent to that the sample will be cross-linked by a KOH IPA solution, and following the cross-linking we will have a washing step, and at the end of it we just allow it to dry once again. So this is the first casting step. You still observe that the sample is essentially a dark droplet, nothing much more than that. It takes around some amount of time to dry. Now an IPA KOH solution will be added, but you observe immediately that it starts showing some sorts of color changes because it's partly cleaned off its ligand, not fully but partly, because there was an alcohol treatment earlier in the process. So casting it simply initiates the process. Now there's an IPA cleaning with KOH IPA solution. The details of the molarities are mentioned. Samples are picked up and it will be washed with KOH at this stage. So sorry, washed with methanol to remove the KOH at this stage. So excess KOH which was still hanging around with IPA has been removed. Reamp out from you. So now the washing is being done. This is mainly with methanol. This is simply to rinse off any alkali which is residual in the system. So this basically also carries off any ligands, etc., along with it. What you observe immediately post that is that there will be drastic changes happening within the film. You can see that the droplet is rather well defined now. So the sample is now dried up. The methanol has evaporated, and as you see, the residue is quite interesting. It changes color as the methanol dries. What you have now is neither something which resembles silver closely nor something which resembles gold closely. You'll notice that the residue is getting white. Now this is now the most tedious part of the sample making. This takes around typically 50 such additions to be repeated. So Dr. Anand will be doing them in due course. Each addition taking the time which you saw it take. This is done, you can do 50 or else you do it till the point when you observe that the resistance is dropped below 10 ohm on these 100 micron electrodes. These do not have a very large contact resistance, that's roughly limiting it by that. The sample at this stage will be white, and if you check the spectrum of it, again you'll have to do it airlessly. and realize that this actually has the resonance which we have talked about. It will be missing the regular plasmon features and at the same time be highly conductive. And what we refer to as R1 state, this sort of a sample does allow you to get partial transitions. We'll be showing you the finished film shortly.